Hey guys, wish you all a very good evening. Quick confirmation, am I audible and is my screen readable? Good evening, Deepit. Awesome. Cool. Do you guys see an OTP somewhere on the screen? Ah, perfect. Thank you so much for confirming. Awesome. Great. Hope you guys have been doing well. If you notice, there's a change in the background, right? It's because I've come back home, like to my parents' home, which is in Thane. So, yeah, slight change in the context, but hopefully it's the same person. Cool. So let's wait for people to join in and we will begin the class soon. Awesome. In the meantime, how are you guys doing? Did you guys have a chance to go through the notebook class? And do you remember what we covered last class? I realized there has been a class skip, right? Apologize for that. I was not feeling well actually. Yeah. Hey, hi, Sean. Nice to see you. So it's been a while. Like there's seriously some sort of flu going on in in Thane at least. A lot of people I know falling ill, kind of. Hmm. Nice, but I'm slowly recovering, so thanks for asking. Cool. Yeah. All right, let's wait. Hey, good evening, Abhijit. Glad you could join in. What's up? Hope everyone is doing well. This is for the new people who are joining in now. Hey, good evening, Narendra. Glad you could join in. Yeah, still better weather compared to last week. I see. That's nice. Yeah. Okay. Good evening, Prasad. Glad you could join in. What's up? Yeah. Cool. I hope everyone has had a chance to go through last time's lecture, the one on Friday. The attendance was a bit lower than usual, but I sincerely hope you guys had a chance to go through that because whatever we are going to, uh, whatever we're going to do today is kind of a continuation of that. So, yeah, just wanted to let everyone know today's class has some prerequisites. Oh, I didn't know that. Okay. So, Anindya says he lives in Airoli, which is close to Thane. Yeah, yeah, yeah. Okay, that's nice. Yeah, the weather is much better. Sorry, I didn't get the context before. Nice. Sure, Narendra. We can definitely do a small recap. I will go through a small recap of the two methods that we had discussed last class, and that will set the context for what's different today. So, mainly, I want you to understand how we are building these vectors and with what objective in mind. Because if we know the objective, right, it becomes obvious how to construct that vector. So, at least that level of understanding we all should have. We will do a small recap. So let's just wait for 30 seconds more. I usually wait till 9:05, right, to start the class. So I'm just waiting till then and we can begin. Cool. Nice to see everyone. Uh, Maybe just 20 seconds more. In the meantime, you know, just wanted to remind everyone what we're doing here, right? Basically, the whole agenda behind natural language processing is to find meaningful representations, and the representations that we want are vector representations because at the end of the day, we want to do some sort of optimization, right? So it's very important to make sure that we have the right representation for the right task. For example, when we were doing computer vision, uh, we made sure that we had embeddings, right? Like the CNN embeddings turned out to be a very good representation because using those embeddings, we were able to do a lot more things. So it was not just about object detection. With the embedding, we were able to do it was not just about object classification. Using the embeddings for classification, we were able to do detection, segmentation, and similarity search, a lot of other things, right? So what becomes important in natural language processing again is to hunt for just the right representation, which will make a lot of tasks easier. Essentially, we want one representation which will work for a lot of tasks. So the way these lectures are designed is we are slowly building our way to the most efficient representations that we know today, right? Okay, but again, that is for later. Let's focus on the task for today, right? Okay, let's do a quick recap. So last class, we had essentially introduced two important terms. There is the corpus, which is nothing but a collection of documents. And then there are documents, which are a collection of sentences. In natural language processing, whatever problem you define, it is very important to specify first what is your corpus and what is your document. Once you are clear about this, it becomes possible to do other things. For example, in the first class of NLP, we had a bunch of tweets, right? The tweets over there were the documents, and the entire collection of tweets was our corpus. In the second class, the data set that we had considered was medium articles. Over there, each article was a document, and the whole collection of documents was a corpus, right? Okay. And as I said just a couple of minutes back, the whole agenda of NLP is to find good vector representations for documents. Specifically, we want to make sure we represent documents inside a corpus, right? Someone may ask the question, should we focus on documents or should we start focusing on the word level, right? Today, we're going to look at that question, okay? That is basically the agenda for today. Should we find good vector representations for documents, or should we dive deeper and look for representations for individual words, right? That is the broad question we're going to try and answer today. Cool. So specifically, this is for Narendra and whoever who probably missed last class. Last class, what we did was we studied two methods of representing documents inside a corpus. Okay, we saw bag of words. Bag of words is like the most naive way of representing documents inside a corpus, right? Broadly speaking, what we do is we take the entire corpus, we look for all the unique words in the corpus, we get rid of all the this thing, right? We get rid of all the stop words in the corpus, and that set of words, which are the unique words for that corpus, is known as the vocabulary, right? A bag of words representation is nothing but a vector which essentially encodes whether a word in the document, whether a word is present in the document or not, right? So we saw two variants of the bag of words model. One is frequency counts, as Abhijit says. The another is the binary form, where we just care about whether it is there in the document or not. So these are the two possible ways we can construct our bag of words representation. And essentially, it is a way to take your document to a vector, right? Okay. Then we saw TF-IDF, which is this thing, term frequency into inverse document frequency. This is a little bit more intelligent than just bag of words. If you guys remember our discussion, term frequency is nothing but bag of words, simply bag of words, right? Where we use frequency counts. So bag of words with frequency counts is nothing but term frequency. Now, in addition to that, we multiply a term over there, which basically tells us how important is this word in terms of the whole corpus, right? The example that I had given last class was, let us say we have a bunch of computer vision papers. Let us assume that we have a bunch of object image classification papers specifically. Over there, the word residual would appear only on networks which came after 2015, right? After the ResNet paper came. So the word residual will appear in that corpus only when we are talking about ResNet, the concept of ResNet. So that is where the inverse document frequency representation would give you a very nice way of picking out these keywords inside the corpus. So residual would have come out as a keyword, or ResNet would have come out as a keyword from that kind of representation. And this is essentially what we studied last class, right? The major takeaway that I want you guys to focus on here is both of these representations are a way for us to take a document to a vector. Today, we're going to do something slightly different. The fundamental change in today's agenda is that we are going to now start thinking of words as vectors, not documents. Entire words are now going to be vectors. Why? Because we want vector representations which capture some meaning, right? The problem with this document to vector thing was the fundamental problem that we saw in the last class was that these document to vector kind of representations don't actually capture relationships between words. Do you guys remember this? Do you guys agree with this statement? Like if I take a document representation, right, it will, yeah, meaning of words or the context may get lost. Exactly, Narendra. So that is the basic problem with this document to vector type of representations. So today what we're going to do is we're going to, for the first time, start thinking of how do I represent words so that the semantic meaning between these words is captured. That is what we're going to study today. The plan for this is we are going to build and invent these techniques together. Honestly speaking, we have covered all the prerequisites to sort of understand, to sort of come up with this representation ourselves. So let us sort of try and invent this together, right? That is the plan for today. Let's see. So, but first, of course, we have to define a business case and we have to see where the need for this would come. So first, let's discuss the business case. Then we will come back and we will invent these techniques together, which will help us convert words to vectors. And these vectors will essentially help us capture semantic meaning. Okay, that's the agenda for today. Let's begin. So this is the problem statement for today, guys. With over 50,000 publications and research papers on the coronavirus family till date, it has become very difficult to search across these documents and get useful insights for medical practitioners, right? This is a fundamental problem. So as a data scientist, let us say at Google, you're tasked with solving this problem with the help of machine learning, okay? You now given a query word. See, last class what we were doing is, given one document, I had to find similarity to other documents, right? Now that is no longer the case. Now I'm telling you that I'm going to give you a short query, okay? A query is nothing but a collection of keywords. You have to use the keywords now to give me relevant documents. So that is the fundamental change in the problem statement that has happened here, okay? Cool. So now let us see how we'll go about this. We have to now think of ways to use some certain keywords to find documents, right? That is the basic change over here. What is the most naive approach that you guys can think, like based on our discussion just now? Can we try and adapt the method that we had discussed last class for this? Any ideas over there? Any ideas over there? Just want to understand if you guys are thinking. Do you guys think I can take that document TF, IDF or bag of words representation to solve this problem? Do you guys think that's possible? Okay, how will you do it? So remember over there we had vectors where document was taken to this thing, right? Can you guys suggest a way? Yeah, cosine similarity of words. Perfect. So Biswarup says, can I now take the document vector? I can find the most commonly occurring words in that document, and then based on the important words over there, I will select cosine similarity over there. So it's like after I have built my representation, I will try to see what would the vector look like for a single document. Right? That is essentially what Biswarup is hinting. That is totally possible. But Biswarup, how will you account for that query? How will you account for the query? What will you do with the query that I give you? Let us say I want to look for all coronavirus papers related to the origin of the virus. Right? I want to now see what do people know about where this virus originated from. So if I just want to search for origin, how will you do that? Ajay is saying embedding. So now I have to figure out a way to take this query vector and embed it in that space of vectors that I had done, right? Yeah, some more features about the word. Okay. So this discussion tells me that, okay, somehow we're getting stuck at one place, right? Yeah. If it's a virus, does it have acne? Yeah, exactly, Vishwarup, right? So the place where we're getting stuck now is there is no way for us to use that query in a very intuitive way, right? So let us think of certain naive strategies first. So one possibility is we can match the keywords from the user queries, right? So let us say there is a query. What I will do is I will look for documents first where the query is most frequent. Then based on that embedding, I will suggest more, right? Yeah. Oh, I see. Ajay is like embedding. I see. That's great, Ajay. So I hope you respect the problem here, right? The problem here is the bag of words and TF IDF representation that we had designed last class was not great for us to be able to work with query statements, right? There's no intuitive way to convert that. The naive approach for that is, can we match keywords from user queries to those that are present in the abstract, right? So now you have to think of ways to create a query vector, which is kind of tedious. So another option is we can do keyword matching, right? So if we were able to sort of get some sort of semantic idea, or look for synonyms that are there in the keywords, and look for the synonyms in all the documents that we have. That's possible, right? It's possible to sort of use that as my first embedding vector, with respect to which I will give you all the other ones, right? So now I hope you guys have understood the need for finding embeddings for vectors. So this discussion was essentially to justify going from a document to vector strategy to a words to vector strategy. Okay, that's the idea here. Cool. So now let us see what data we have available for this problem. Everyone with me so far? Do you guys agree the need for going for a different type of representation now? Okay, just checking. Awesome. Cool. So let's proceed. Let's first look at the data set that we have available. Then what we have to essentially do is build a querying system around this database. Okay, so let's see. The data set that we have is basically open research data set containing publications and research papers related to COVID. So this was essentially a Kaggle competition. The link is available here. If you guys want to sort of explore this competition, I'll be pasting this link right away in the chat window. You could take a look at this Kaggle competition for where the data comes from. But what we're going to do now is we're going to explore the data set a little bit. Okay. Before we explore the data set a little bit, let's sort of see here. We have to sort of download this one extra library today. The name of this library is LangDetect. The job of this library is to tell you which language is the paper from. Okay. It turns out that in this document, right, there are papers in multiple different languages. So since we are speaking in English and we're most comfortable with English, we're going to try and solve the problem only for English papers today. So that is one additional layer of complexity that is there for today. This library essentially gives you a very nice solution for detecting which language, and we're going to use that, okay, to make our life easier. Okay. The rest of this is pretty common. The rest of the imports are pretty common. Now let us see what our data set looks like. So the first thing that we have is this CORD UID. You might be wondering what is CORD. CORD is basically this Collaborative Research and Dissemination Organization. So this is an organization which basically indexes papers about research papers and makes it easy to find, right? That is the job of this organization. This is the UID corresponding to that. Over here, next I have this SHA. This SHA is a hash map which allows me to check whether my document has been downloaded properly. You have the source journal. So over here, PMC is the PubMed this thing journal. So this will essentially tell you from where is this paper coming from, right? Then we have the title of the paper. We have the DOI. DOI is the data object identification number, like digital object identification number. It's a unique number which identifies resources like PDFs or code or something like that, right? Then we have PMC ID, which is PMC Journal's ID for its papers. You have the PubMed ID. PubMed is another organization which organizes papers and makes it easier to search for. Then you have these licenses. You have these abstracts, etc. Right? We have a lot of features over here. Out of all these other features, right, guys, the other features that are here I'm skipping because they're essentially metadata. We don't really need to worry about these. What we have to focus on over here is just the text columns, right? So broadly speaking, which are the two most important columns, do you think? Which are the two most important columns according to you for our task, the searching task? What do you guys think? Title is one, perfect, Indradeep, and abstract, right? Why abstract? Because guys, generally in an abstract, you have a summary of the paper. It's the job of the researcher to sort of give a summary which will essentially tell three important things about the paper, okay? Where did the paper come from? What are the major contributions of the paper? And what are the what are the results? Like a summary of the results. What is the exact this thing that is there, right? The exact delta that is there from existing research. So that has to be there in the abstract. So what we're going to try and do today is we're going to search for documents based on the contents of the abstract, right? So we have to choose between title and abstract. If we had to choose between title and abstract, obviously the abstract will be nicer because it has all of these important details inside it, right? So whatever representation that we're going to build today is going to be based on the title and the abstract. Okay, perfect. Cool. So Ajay, I agree that DOI is important, but we're going to avoid the DOI because we can't really do any text processing here, right? The DOI is this weird looking number. We can't really make sense of this unless we know the details of how this is generated. So we're going to focus only on the text and abstract. Okay, cool. So this is what we're going to do, and we're going to quickly see if this has any missing data. It does not. We have basically these 100,000 odd papers in this database. If you notice, guys, this data set is a bit large, right? It's a 1.65 GB data set. Yeah. Oh, okay. Ajay says we can return the DOI. Perfect. Yes, Ajay, we can return the DOI. So in the return statement, we can give the DOI back. What I was asking you before was what will we use in our processing, right? So DOI we won't use. Okay, cool. So now let's load the data set. Let's sort of see what this looks like. Okay, this is something that we've seen already. Now, essentially what we're going to do is we're going to start discussing what is the way for us to solve this problem, right? So let us discuss some naive strategies and let us try to come up with ways for us to arrive at word embeddings. Okay, cool. So let's do that. So first questions first. What are the representations that we know and should we make any changes there, right? Okay. So broadly speaking, now our data set looks like this. We have different documents, document 1, document 2, so on, till document N, where each document over here is a paper, right? Each of these documents are papers. And specifically, they're not papers, but they're paper abstracts. Okay. The collection of the whole document is our corpus. Let us represent the size of this corpus as small n, and let us sort of think of the representation for each document over here as an k-dimensional vector, or let us say a d-dimensional vector. Okay, cool. So guys, if I had to construct a bag of words representation for this corpus, what would be the dimensions of my matrix? Can you guys tell me? If I had to do a bag of words representation, perfect. It would be n cross p, right? I would basically have all the documents as rows. I would have all the I would have the words as the columns, and this d is nothing but the size of my vocabulary here, right? Size of the vocabulary. Okay, cool. Yes, Vishwarup, I did say vector representations for each words, but we're slowly going to go there, right? First, we're going to try and see what we already know, and then we're going to build on top of that. So just wanted to do that. Okay, cool. So our bag of words representation will basically look like this. This is an n cross d matrix. This is my bag of words representation. Okay. So guys, before we go on to better representations, let us try and apply what we know to solve the problem at this stage, right? I'm sure you guys have gone through the ML2 module where you learned something about recommender systems, right? So if let us sort of do a quick recap of that lecture, right? So if you guys remember, the concrete example that you guys had studied in the recommender systems class was movie recommendations. Am I right about this? Do you guys vaguely remember what the movie recommendation thing was? Okay, so movie recommendations was the topic over there. What approach had you guys followed? So movie recommendations broadly, right? You had a matrix representation like this, which gave you different genres of different movies. Okay, what was the approach that you had followed to build a recommender system around this? I want a keyword, right? I want the keyword for the approach followed. Matrix factorization or decomposition. Perfect. Okay, matrix factorization was the approach followed, right? Matrix factorization. So, or collaborative filtering, of course. So let us for now, just for a short while, focus on the matrix factorization approach here. If I had to apply matrix factorization, first of all, why do we apply matrix factorization? Our intention is to get an embedding, right? the embedding contains some useful information about the relationship between the rows and the columns, right? The row and column representations, we want some relationship there. So we typically do a matrix factorization. So if I had to do a matrix factorization, how would I do it? I would start with n cross the matrix. So let me call this matrix as, let us say my R matrix. Okay, this is the representation matrix. I would essentially divide this into two matrices, right? I would represent this as a product of two matrices, where the dimensions of the first matrix can be thought of as n cross k, and the dimensions of the next matrix could be thought of as k cross d, right? Essentially, over here, the k dimension that I have here, right? K is the column dimension in this matrix. This column dimension will essentially give me some useful information here. Okay. So now I want you guys to tell me, if I have n documents in my corpus, right? If I do this kind of a matrix factorization, the matrix A, can I interpret this matrix A as a latent representation of my document vectors? Can I think of it that way? Just based on dimensions. No, we're not worried about the technical details. For now, I just want you to study the dimensions and tell me, can we think of this as latent representation for my documents? We can, right? Similarly, this is a latent representation for my words, if you notice. Why? Because it's k cross d. Now, every column in this B matrix is going to be a d-dimensional matrix. It's going to be the length of the vocabulary that I have. And this is essentially going to give me a embedding for the words that I have in my document, right? Okay. So this is how the matrix factorization approach to this problem would have followed. What we have to do now is sort of think of a way for us to use this idea and build on top of it to solve our current problem. Okay, to solve our current problem. Okay, so let us use matrix factorization as the base technique, and whatever we will build is going to be on top of this. So let's bring this matrix factorization here, and let's bring this matrix of bag of words over there, right? Okay, cool. So first, let's solve the most obvious problem, which Biswaroop had started off asking me about, which is the dimensions of this matrix, right? So right now, the R matrix that I'm using is nothing but a sort of bag of words representation where I'm not able to capture relationships between words. Okay. Now let us think of a very nice strategy to come up with a representation which tells me how important is a word with respect to other words. Okay. So to do that, let us take this example of a sentence. Let's take an example of a sentence. Okay. Can somebody give me a sentence about computer vision or a question in computer vision? Let us take something like, how is object detection related to segmentation? Right? Okay. So this is the example sentence that I'm going to take. Do you guys realize that this word object detection, right? The word object and the word detection appear very often together. Why should they appear often together? Because this is actually the name of a problem, right? We want to get a bounding box on the objects that are present in an image, right? So this object detection is basically a pair of words which I can say appear a lot together. Do you guys agree or disagree? Do you guys agree or disagree? That they appear a lot together. Okay, cool. So now comes the question, how do I capture this relationship? Right? How do I capture this relationship? The name of this relationship is proximity. Okay? Proximity. I'm going to call this proximity. The meaning of the word proximity is how close are these words present with respect to each other. And Biswaroop in private chat has told me, I can think of this as a bigram or an n-gram where I set my n equal to 2. Okay. So is everyone comfortable with the notion of an n-gram? Some of you who may have missed last class may not know this. But if you're comfortable, if you don't know what this n-gram means, please let me know right away. I will explain what this is, but looks like no one is confused about this. So let's move on. Okay. So one way for me to do it is I can detect n-grams here, right? But this n-gram is with n equal to 2, right? Do you guys remember the convolution operation that we used to have in images? So if I had an image, right, the convolution operation would basically take place with respect to a kernel, right? And the kernel was usually an odd size kernel, okay? What we used to do was we used to put a sliding window. We used to think of this kernel as a sliding window over my image so that everything that all the pixels which appear close together are captured by this kernel, right? Can I now think of a way to use this kernel like concept over here instead of n-grams, right? I know what n-grams are, but I don't want to use n-grams right now. I want to think about this slightly differently. The problem with n-grams is it will basically form pairs, triplets, or collections of words, right? But it does not really tell you the positional information in the sense that the word detection over here is at position t, right? The word object is occurring before this word, right? It is at t minus 1. Similarly, the word related over here is occurring at t plus 1, right? Similarly, here I have t minus 2. Here I have t plus 2, right? Whenever I'm talking about positional information, it is important for me to also keep in mind whether the word that I'm having with respect to this is coming before this or after this, right? That's the basic intention here. So now onwards, what I'm going to do is I'm going to define a way to do a sliding window approach on this sentence. What I'm going to say is every time I'm looking at a word of interest, right? Yeah, every time I look at a word of interest, the words which are present before it, right? The words which are present before it will come over here on this side. The words which are present after it will come over here. So effectively what I have over here now is a window of size 5, right? I have a window of length 5. The window is centered around this word detection, and the window is now capturing the relationship of this word detection with respect to object is, and it's also capturing the relationship of this with respect to related and to, okay? So this is the strategy that I'm now going to apply to sort of build my representation. So this is how, using this window concept, this is how we are moving away from a document level vector representation to a word level vector representation. See, now it's no longer important for me to know which document these words are coming from. I'm now trying to capture the relationship between one word and another word, right? So now I have to think of putting these relationships in a matrix where all the rows are also words, okay? All the rows are also words, all the columns are also words. Agree or disagree? Agree or disagree? Does this representation make sense? I want to now make a matrix which has words on the rows also, words on the columns also. Every entry which is there inside this matrix, right? Every entry inside this matrix is essentially going to capture the relationship between the word which is there on the row position and the word which is there on the column position, right? That's the idea. Yes, Indradeep, perfect. This is a square matrix. The size of the square matrix is now going to be mod V cross mod V, right? Where V is nothing but the set containing, it's the vocabulary set, sorry. It's the vocabulary set, right? Okay. So I'm now going to stop thinking of doing matrix factorization on this matrix, and I'm going to start thinking of doing matrix factorization on a matrix which looks like this, okay? The intention behind constructing a matrix like this is I'm going to define a sliding window. I'm going to find a way to represent the relationship between these words with respect to that window, and the number, like the number I'm going to put over there is going to depend on this thing over here, right? The number is going to depend on the number is going to depend on how many times has this word object occurred with detection, right? How many times has this word is occurred with detection? How many times has this word related occurred with detection? So this is essentially the intuition behind constructing a matrix representation like this. Okay, cool. So I'm going to pause here. If anyone has any doubts up to this point, you can ask me. Otherwise, we're going to continue thinking about matrix factorization on a representation like this. Okay, cool. Okay, any doubts? I suppose not. So let's move on. Okay, looks like there are no doubts. Let's move on. Now what I'm going to do is I'm going to take this word matrix here, right? This is a word to word matrix, something like a word to word matrix. I'm going to start with this matrix. I'm going to now call this matrix R. The dimensions of this matrix is mod V cross mod V, right? Mod V cross mod V. And I'm going to essentially say this R mod V cross mod V, this thing, I'm going to apply some sort of matrix decomposition here. Okay. So guys, in like historically speaking, right, the matrix decomposition, which is the most useful for problems like this to make embedding like problems, is the singular value decomposition method. Singular value decomposition method. Okay. How many people in class have not heard of this method before? This method is called SVD. Okay, singular value okay, so there are some people who have not heard about this type of matrix decomposition. So let us spend 5 minutes to try and understand what is happening in singular value decomposition. Okay, cool. So guys, generally what happens in singular value decomposition is, if you give me any matrix, okay, you can give me any matrix of any dimensions. Ajay heard but forgot the concept. Don't worry, Ajay. Let us recollect this, right? So if you give me a matrix which is of any dimension, m cross n, okay, any dimension, the singular value decomposition method, what it does is, it will take this matrix and it will represent this matrix as the product of three matrices. Typically, we say that these matrices are U, sigma, and V. Okay, this is the general notation that we use for singular value decomposition. This vector U has dimensions m cross k. This vector sigma has dimensions k cross k, and this vector V has dimensions what? What should this be? Just checking. Do you guys remember matrix multiplication? What should this be? N, right? Perfect. So this should be N, of course. This should be N. Cool. So typically, whenever we apply singular value decomposition on a matrix, right, the K over here, what becomes important is this number K over here. Okay. What is important for us to understand is this number K basically tells us what is the inherent dimensionality of A. Okay. What is the inherent dimensionality of A? What does this mean? Let me explain. Okay. Let me explain this. Let us say I have a 3D space. Let us first say I have a 3D space. But in this 3D space, I simply have one plane over here. Okay. I simply have a plane which is lying in this 3D space, right? Can you guys tell me what is the dimensionality of the plane in this 3D space? What is the dimensionality of the plane in this 3D space? Guys, 2, right? It has to be 2. This is a 2D object which is living inside a 3D space. Right? So if I now take all the vectors, okay, guys, what I'm going to do now is I'm going to take all the vectors which are pointing to some point which is lying on this plane. Okay, I consider the collection of all vectors which are lying on this plane. If I look at that collection, if I just take all these vectors and I put them inside this set called P, okay, this P is nothing but a plane, and inside this are basically all vectors lying on the plane, right? Okay. So guys, can you tell me, if I have to write the coordinates of these vectors, how many numbers do I need? What will the address look like for these vectors? What will the address look like? What will the address will require 3 numbers, right? I will need X, Y, and Z to represent this, right? I will need X, Y, and Z to represent this. But, okay, but the plane itself, the collection of vectors is actually living in 2 dimensions. right? The collection of vectors is actually living in 2 dimensions. So do you now see that even if I have vectors which are m dimensional or n dimensional, the actual inherent dimension can be less than this m or less than this n, right? This is the idea I'm going for here, guys. Whenever I'm applying SVD, what I have to look for is how can I break down my matrix so that I can get hold of this inherent dimensionality of n. Okay, how can I now do something so that I can get to the inherent dimensionality? Over here, this is very clear, right? Over here in this picture, it is very clear. The inherent dimensionality of this plane is 2, but the address requires 3 dimensions. Typically, when we are trying to look for latent vectors, we are usually trying to reduce the dimension, right? Whenever we studied PCA, whenever we studied TSNE, we saw that our objective is to reduce the dimensionality. So that is how SVD is related to all the concepts that we have learned before. Okay, SVD is essentially a method which can be used to find latent representations. What is special about SVD is that it automatically figures out what should the size of that latent dimension be. Okay, it automatically figures out. We don't have any control on this K. SVD will tell us what this K is. Okay, and this is why it's very popular. Okay, now what we are going to do is we are going to take this word matrix, right? This matrix representation that we have created, where we have put all the words in the rows, all the words in the columns. We're going to take this and we're going to apply SVD to get the following representation: U sigma V. Okay, so if we were building a recommender system using the knowledge that we've had so far, this is what we would have done, right? We would have taken this word matrix, we would have applied SVD. We don't have to worry about the details. Okay, there are enough packages available online and in Python which will do this for us automatically, right? So you can look those up. You'll find those packages in NumPy itself. NumPy.linalg will have it. So that is where you should look. Typically what we would do is we would take this, we would take the U matrix over here, right? And we would say this, the rows of this matrix, right? The rows of, sorry, not the rows, right? M rows, K columns. The K columns, yeah. So the rows, okay, yes. So if this is M cross K, right? M is basically mod V here, right? And this would be K. Okay, what we would do over here is we would apply SVD on this representation and we would get this. Okay, this is how we would solve the problem. Does this approach seem sound to everyone? Is everyone following me with me so far? Smaller the K, the better. Yes, Bishwaru, absolutely. Smaller the K, the better. In these kinds of situations, it's always better to have small Ks. So I'll tell you what. Okay, guys, can you tell me, do you think this matrix will be sparse? Do you think this matrix will be sparse? Word to words? It may be possible that some words are never appear together, right? It's possible that some words never appear together. So we can expect this matrix to be sparse, right? Generally for sparse matrices, it is almost guaranteed that the K will be much lesser than M and N. This is generally a guarantee for sparse matrices. So we're set here. Okay, cool. Yeah. We only take the U matrix and discard the V matrix. So Indradeep, there is actually a relationship between this U and V matrices. You can use either of them. You can actually use either of them. If we're using the U matrix, you have to look at the rows. If we're using the V matrix, you have to look at the columns. It doesn't matter which one we pick. There is a very nice relationship between them. So it's okay, whichever we pick. Okay, cool. Okay, now coming back to the point, guys, for the current problem at hand, right? The current problem at hand, we have 1 lakh papers, and it's possible that our vocabulary size will be too large. It will be too large for us to actually apply SVD. SVD is an operation which takes M into N, like the time complexity for SVD is very high. It is actually this product of this, like it's on the order of the product of these dimensions. Okay, which is why it becomes very, very difficult to actually apply SVD to do this. So the ideal method would have been to apply SVD, but SVD becomes very, very computationally inefficient for us to apply. So that is why what people did was they applied SVD to solve problems like this. They saw that it was very effective, but then they were not able to move beyond a certain size of corpus. Okay, they were able to do this very nicely for a small corpus set, but it turned out that they couldn't do this because of computational reasons for very large corpuses. So instead, they came up with a different solution for this. Okay, they came up with a different solution for this, and the solution involved neural networks. Okay, neural network solution is what they came up with. It turns out that it's more efficient to train a neural network to do this task than to actually apply SVD to learn something like this, right? So what we're now going to do is we're going to discuss a sort of neural network approach to solve this problem. Okay, so if you guys have been paying attention, you may have noticed that what I basically want to do is I want to reduce the dimensionality of my vocabulary set, right? I want to reduce that dimensionality. From all the neural network architectures that you know, which architecture is the best for doing dimensionality reduction? Autoencoder. Yes, Indradeep, exactly, right? So the autoencoder is the best possible neural network for doing this, for doing dimensionality reduction. So what we're now going to see is we're going to try and apply an autoencoder solution for this. For dimensionality reduction. Okay, we're now going to try and design an autoencoder which is able to take in a word. Okay, it's going to take in a word, it's going to reduce the dimensionality of that word, and it is essentially going to try to predict something. Okay, how to design this autoencoder, how to go about building a data set, all of those considerations will now come. Okay, just want a quick confirmation. Is everyone with me so far? Our objective is basically doing dimensionality reduction to find embeddings. Why are we doing this? Because we want to recommend based on the semantic meaning of words, right? So after all this exploration of different techniques, we have said that the most efficient way for us to do this is an autoencoder. So let's proceed with seeing how we can build an autoencoder solution for this thing, for dimensionality reduction. In fact, the name of this autoencoder solution is known as Word2Vec. This is the name that people give to autoencoders which gives embeddings, word embeddings specifically. Okay, cool. Yeah. Oh, I see. Bishwarup has a concern, guys. He did not understand how we moved from document level to word level. Bishwarup, we moved from document level to word level on this slide. Okay, we moved from document to word level on this slide. Basically, before what we had was this N cross D matrix, right? The N cross D matrix had documents encoded in the rows, but we saw that the document representation was not effective because it was not capturing relationship between words, right? So we wanted to fix that problem. How did we fix that problem? We said, let us use a kernel which is moving along my sentence or along my document. Let me define this kernel. So just like convolution used to move a kernel along this image, right? And it used to capture relationships between pixels which were close by. Same way, we have this kernel here now. Oh, okay, it's not okay. This kernel will basically move across my sentence, and it will basically tell me which words are close together. I have not yet told you how I can use this to create a number. That is still missing. I'm going to talk about it now. If that is a confusion, please wait for some more time. I'm going to come to that. Yeah, okay. These vectors are the new embeddings. Yes, these vectors are the new embeddings. The embedding is not this. The embedding is not over here. The embedding is in the matrix factorized version of this representation. So now the details of that is what we're going to discuss. The main intuition here behind Word2Vec is I want to apply something like SVD to get embedding vectors. SVD is too inefficient for me, so I'm going to go for a more efficient approach. The more efficient approach is training an autoencoder. So that is where we are. Okay, cool. So now let us start discussing how to build this autoencoder. What are the different strategies we can use to sort of, what are the different strategies we can use to prepare the data set, learn that, and everything, right? Okay. But at the end of the day, what I want you guys to remember is this is an autoencoder. Okay, cool. So let's get there. So this is an example of SVD being applied to do this. This is an example of word embeddings. So again, you can use either this or that. So essentially this thing, but yeah, the problem with SVD is that it's extremely computationally expensive, very troublesome to compute. So let us now move on to Word2Vec. So Word2Vec is the name given to an autoencoder architecture, which will basically help me capture the relationship between words which occur together. Okay, very simply put, that is what Word2Vec is. Now let us see how we do it. Okay, cool. So the way Word2Vec works is it is going to take a large corpus of data. It is going to take each word. It's going to use that sliding window approach to move through these documents. And using those sliding window approaches, it is going to give us an embedding vector, right? So this is the mapping between one word to one vector. And what is nice here is that in Word2Vec, we have control over the size of this. Okay. So let us discuss what are the possible architectures over here, right? So typically, an autoencoder architecture looks like this, right? I have an input vector here. So I'll call this my input vector. Then I have something which is known as a hidden layer. And then I have an output vector, right? This is essentially how my autoencoder architecture works. Cool? Okay. What do you think should be the dimension of the input vector? Anindya's question is, how do we learn to optimize window size? Anindya, it's a lot of trial and error. See, these the window size becomes a hyperparameter for this method. And today, we're like in the example, right, when we're actually building our solution, we will see how to fix that, right? So we can decide based on the performance of that document finally. So tuning that becomes an issue. We'll see that later. For now, can you guys help me guess the dimensions of this neural network? Yeah, mod v, right? My input vector has to be mod v, where v is again my vocabulary size, right? Okay. The input vector to this neural network, how do you think I should encode it? If it's mod v, can I say that my input vector is one hot encoded? Can I say it's one hot encoded? Right? I can say that it's one hot encoded. Okay. So one hot encoded input vector is there. So this one hot encoded input vector is basically going to be a 1 for the word of our interest, whichever we want to embed, and it is going to be 0 for everything else. So that is how the input vector is going to look like. The output vector, what do you guys think the output vector should look like? Did you notice that we have a sliding window now? Did you notice that we have a sliding window? Is it okay if I put my output vector as a 1 for all the words which are close to this detection? Is it okay if I do that? What do you guys think? Is it okay if I take all these words, right? I create my output vector for this training example, putting a 1 for the word is, putting 1 for object, putting 1 for related, putting 1 for to, right? I'm going to put 1 for all of these now, and that is how I'm going to design my output vector, right? So it's going to have 1, 1, 1, 1. The number of ones it's going to have is equal to the window size that we have chosen. A representation or as ones wherever words has ones for words inside the sliding window. Okay. So broadly speaking, my Word2Vec architecture looks like this. Okay. my Word2Vec architecture looks like this. I have total freedom on if I want to put more hidden layers in between these neural networks. But in Word2Vec, right, in the traditional Word2Vec paper, the dimensionality of this was simply one. Uh, right, there was simply just one hidden layer in the original Word2Vec paper. So now in Word2Vec, what we're going to do is we're going to just keep one hidden layer and we're going to consider this shallow neural network to do our job. Okay. So this is what my Word2Vec looks like. Now the question is, how do I encode this, right? How do I do the training? How do I prepare my training data set a loss function and train it, right? Those questions is what we have to answer. So let us now talk about that. Let us now talk about what are the ways to learn these embeddings. Now, guys, broadly speaking, there are two ways to learn the embedding. Okay, there are two fundamental ways to learn the embeddings, and the best way for me to explain this is to talk about it from the context of our school days. Okay, so do you guys remember in our school days, in all these English, Hindi, all these language papers, right? We had two types of tasks. Like for us, we had two types of tasks. Do you guys remember fill in the blanks? Fill in the blanks. You guys remember, right? Okay. So let's take an example of that. ResNet is a type of dash neural network. Can you guys tell me what should the blank be here? Sean is saying, talking about SIBO, glow yes, Sean. And that's what I'm talking about. Biswarup is saying shallow convolutional network. Hey, no, man. It's not shallow, na? It's convolutional. ResNet is a type of convolutional neural network, right? So throughout our computer vision classes, you used to see the CNN appearing together, right? So I was testing if in your brain there is that embedding, right? Okay. So mainly what I want you guys to notice here is in the fill in the blank type of question, what is given to us is the words which are close by, right? If you think about it, I am given these words which are close to this word which is missing, right? The task is basically to fill in the missing word. So now what we can do is we can get our neural network to solve this kind of a problem. Okay. We can take this sliding window. We can take the word of interest and remove it. Okay. We can remove that word of interest and we can ask our neural network to predict based on these words which are given to me. How? So if I just give my neural network is object dash related to, and I ask my neural network what word is missing here, right? That is one type of task I can train my Word2Vec neural network to do. Okay, this is an example of fill in the blanks type of question. And in the Word2Vec literature, right? In Word2Vec literature, this is known as the continuous bag of words representation. Okay, continuous bag of words representation is nothing but fill in the blanks. Given W of t minus 2, W of t minus 1, W of t plus 1, and W of t plus 2, we have to get our network to predict what is the most probable word which is there in the blank over here. Okay, that is the job over here. Okay, so this fill in the blanks type of task is the same as the continuous bag of words model. For Word2Vec. Okay. Yeah. So Indradeep is asking me why is it called continuous? Because Indradeep, essentially, if you think about it, right, bag of words did not take bag of word did not take word relationships into account. In this bag of words representation, we want to establish continuity, right? So it is like, since I'm asking you to fill in the blank, I'm asking you what word can I introduce here so that this makes sense? What word can I introduce here so that it becomes continuous? That's the idea. Okay. So that is fill in the blanks. Now let us talk about the opposite problem, right? The other type of question we were asked in our 10th, 12th standard was, write an essay on so we used to be given one topic word, right? We used to be given a topic word. Let us say I give you the topic word as convolutional. Okay. And now I am asking you, can you give me some other keywords which can appear before this or after this, right? So this is essentially like I'm asking you how to build an essay. Okay. I'm essentially asking you how to build an essay around this word convolutional. Okay. So this type of a task, right, where I give you a keyword and I ask you to write some essay on top of that, this type is known as the other method, which is skipgram. Okay. So the skipgram task is where I will give you one word and your task, your job would be to add words before this and after this. Okay. So this is the skipgram representation. Skipgram strategy, sorry. It's a strategy for training your Word2Vec. Okay. So let's pause here and let's think about this intuitively. Okay. So guys, we have let us make sure we are on the same page, right? So far, what have we seen? We wanted to obtain embeddings for words. We decided we are going to use a neural network to do this. We decided we will use an autoencoder architecture. Now the question is, how do I train this autoencoder, right? And I'm giving you two strategies now. One way to train this autoencoder is you take words and ask it to fill in the blank, or you can give one word and ask it to predict what words are before it and after it, right? Okay. So we have this fill in the blank strategy and we have this write an essay type of strategy. Between 1 and 2, which one do you think is more difficult? Which one do you think, or which one did you feel was more difficult? Do you guys agree 2 is more difficult? It's generally very difficult to write an essay, right? So do you guys agree that if I use strategy 2 to train my network, I'm asking my neural network to do a slightly more challenging task? Is everyone in agreement with this? Right? Is everyone in agreement? Please hit yes if you agree. I just want to know if we're on the same page, guys. Okay. So it looks like this is a slightly more difficult task because now I'm asking my neural network to tell me words before and after, right? So that's why writing an essay is a slightly more difficult task. So intuitively speaking, by looking at it as fill in the blanks and write an essay on type of task, it looks like the second approach will help us learn better representations, right? So let's see now. So let us now agree that, okay, intuitively it looks like skipgram will be better than continuous bag of words. Let us see if this is actually the case, right? Let's go ahead and see that. Cool. So in continuous bag of words architecture, the task is fill in the blanks. In skipgram, the task is write an essay, right? So let us take a deep dive into both of these strategies and later on we will see which one is better. Okay, cool. So let's deep dive into CBOW for now. CBOW is continuous bag of words, and let's talk about how this is done. Okay. So once again, the input that I feed into my neural network is this vector X. This vector X is a one-hot encoded vector, right? So this vector is put as the input to this layer. There is a single hidden layer. You have this weights and biases associated with this single layer. The activation function that we typically use for this task is ReLU over here. Okay. Once we have parsed it through this hidden layer, we have to give an output layer, right? We have to give an output layer. In this output layer, the label that I'm going to give this network is basically a 1. I'm going to put a 1 in that vector for all the things which are close by. Okay. So I'm not going to put a 1 for detection, of course, because that is what I wanted to take as input. So giving detection as input, I wanted to sort of, sorry, my bad, the other way around. Given is object related to as input, I wanted to predict detection, right? So what I will do is in the input vector, I will give 4 numbers over here if my window size is 5. In the output layer, I'm going to expect a one-hot encoded label. The one-hot encoded label is essentially the fill in the blank answer over there, right? So this is how I'm going to create my data set for training, and I'm going to train this. Now, of course, whenever we want to do these kinds of prediction problems, the best loss function to use is the softmax, because the softmax will basically give me probability values, right? It will tell me what does this network think is the most probable value for the fill in the blank, right? So softmax is the output layer. We're going to use the softmax nonlinearity in our output layer, and that is how we're going to train things. Cool. Okay, so let's sort of see how to generate training data for this. So we'll take these three examples. So for example, here in C0 we have the cute cat jumps over the lazy dog. The C over here is essentially defining a window size. Okay, how is it defining a window size? Let's see. So if I put C equal to 0, it's like I'm telling my algorithm to just take the center word. If I put C equal to 1, I'm telling my algorithm to take one word before and one word after. And for C equal to 2, I'm asking it to take two words before and two words after, right? This is how I'm going to build my training data for training the CBOW model. Okay. Any doubts so far? Is this part clear? How I'm going to generate training data? Okay, cool. Let's proceed. So let us continue discussing how CBOW will work. This I believe is something you've studied in your neural networks class, right? It's kind of straightforward how the training of this will work. You will essentially go to Keras, you will implement this very simple architecture using either your functional or your what do you say, the linear what is the name that we give it? Sequential API, right? Yeah, sequential API. So you'll use one of those to implement this. You will sort of set everything up, and you will build a function which is able to take these kinds of things and train on that, right? And training would be quite straightforward. We'll keep doing this till we achieve a certain level of accuracy in our output layer, and then whatever survives, right? The network that we get after training, we're going to extract the hidden layer from that network, and we're going to use this now as our embedding. Okay, this is now going to be our embedding, right? That is how we would go ahead with the training of this one. Okay, cool. Now, if you guys notice, this is like a prediction problem, right? So if it's a prediction problem, what is the loss function that we typically use for prediction problems? If softmax is my output nonlinearity, which loss function makes the most sense? CCE. Perfect. So categorical cross entropy loss will make the most sense over here, right? So the loss function that I will use for training this neural network for CBOW is the categorical cross entropy loss. It looks like this. Does anyone require any recap or any explanation around this? Is it okay if I proceed? Okay, cool. So I hope we're all comfortable with what the categorical cross entropy is. This is what I will use to essentially train my network. Okay. So what I will give as are the context words vector. CBOW will take that. It will give a prediction for the center word. It will compare it with the actual center word. It will compute the loss function. It will minimize this loss function by adjusting these parameters, right? We have very few parameters in this network, and typically that is how it goes. Okay. Now, this was one of the most early methods of doing Word2Vec. And actually, guys, it turns out that it's not that great for embeddings. Okay. This was one of the first methods that was proposed, but it has a certain shortcoming. It has a few shortcomings. The shortcomings is this. Okay. This kind of a network tends to overfit on the frequency. Why overfit? Because like I said, right, in fill in the blanks, there are only certain words which make sense, right? You're not really required to sort of use a lot of contextual information. The only contextual information you'll use is at the sentence level, right? So as a task itself, the CBOW strategy is a bit lacking. And why is it lacking? Because of our intuition that essay writing is more difficult than fill in the blanks, right? For the same reason, CBOW is usually not used in practice because of the way the task is set up. It does not produce good representations for the rare words. So for example, let us say that there is this paper on COVID where they study a certain gene, okay? And let us say that is the first paper where they've discovered that gene, and only 2 or 3 papers have worked on top of that, right? Do you guys think my network will prioritize learning that keyword, the name for that new gene they found in the virus? Do you think that's really going to happen? Not really, right? It's not going to prioritize that. It's going to prioritize trying to fill in the blanks for more common words. Okay, that is why fundamentally CBOW is not a very effective method in producing good representations. Okay, which is why people came up with the skip gram idea. Okay, this is why we generally prefer the skip gram idea. Okay, because skipgram allows you to to do skipgram properly, it is required for you to predict words around the keyword, right? That is what makes it more effective, and that is why we sort of go for skipgram, for the skipgram strategy for training our Word2Vec. Okay, cool. So it is 1 hour 10 minutes now. If it's okay with you, is this a good time for a break? Can we take a 5-minute break here? And once we come back, we'll talk about the skipgram strategy for training stuff. Okay, cool. So let's do that. So what I'm going to do is I'm going to sort of leave this over here on screen. I just want you guys to be very familiar with these strategies for training our Word2Vecs. And once we come back, we will see how to do skipgram. How do we get our networks to write essays, right? That is also moving slightly towards what ChatGPT does, right? So yeah, slightly more intelligent. Let's do that. So see you guys in 5 minutes. Once we come back, smarter stuff. And we're back. Can I get a quick confirmation if you guys are back? Uh, okay, some people are back. Okay, quite a few people are back. Awesome. And one person wants to make me laugh. Awesome. Great. Cool. So let's resume our discussion, right? So before we went for a break, we saw that the continuous bag of words model, it is kind of a simple task, and because it's a simple task, our network tends to overfit. It does. There are two problems with continuous bag of words. It tends to overfit, and it tends to ignore rare words, right? So now to fix that problem, we have to make our train a neural network with a slightly more complicated task. So let's talk about that. So to achieve skip gram, right? It now sort of becomes important for us to change the architecture of our network a little bit. Okay. So let me quickly show you what the new architecture is going to look like, and let us see. Right. So now what I'm going to do is I'm going to input a one hot encoded label, one hot encoded vector. The place where I'm going to put that one is the word with respect to which I want to write an essay, right? So for example, I will put one for wherever convolutional is in that this thing, and I will pass it through this. Once again, I'm only going to have one hidden layer. The major change is in the output layer. Okay. Now I'm going to actually sample multiple outputs. Why am I sampling multiple outputs? Because I want to encode positional information over here, right? So I essentially have one output for t minus 2, then I have, sorry, this is for t minus 1, then this will be for t minus 2, and then this will be for t minus 3, and so on, right? So this is how I will essentially represent my skip gram. Do you guys realize why I need this separate outputs? Why can I not just get one single vector with multiple ones? Any idea? Any idea as to why that's happening? Yeah, different words, right? If I now start giving you a one hot encoded vector where multiple ones are there, and I try to train this network with, say, the categorical cross entropy loss, right? The network will get confused because I'm asking it to give out probability values which are 5, but probability values have to sum up to 1, right? So that becomes the issue here. It now becomes important for me to train with probability 1 for this position, probability 1 for this position, probability 1 for this position, and so on, right? So there are different strategies for training this. One type of strategy would be where I encode positional information. Another type of strategy is where I just expect it to give those words, where the order won't matter, right? For now, let us see which one we will use for our actual training, right? Okay. So the skip gram will require a slight change in our architecture. Let us see now what we are going to do with this. So coming back, how do we generate training examples for skip gram? Right? So given an input have over here, what I want my network to do is give me I and A as two different outputs of that, right? Similarly, if I give I want it to give have and big as the outputs over there. Similarly, if I have big, I wanted to give A and dog as the outputs over there. So this is how I will essentially create training data for training my skip gram connection. I will again pass a sliding window. From the sliding window, I'm going to select the word. I'm going to keep the central word as the input vector. The related words in the sliding window, I'm going to keep as the output vectors, and I'm going to carry out my training that way. Okay. This is how I will essentially carry out the training of skip gram at a high level. Now, let us dive a little deeper into this. Okay. Let us kind of dive a little deeper into this. If you guys notice, right? If you guys notice, my job now is to predict multiple things. So do you think a categorical cross entropy loss still makes sense for me? Do you guys think that still makes sense? It shouldn't make sense anymore, right? Because the categorical cross entropy loss expects your output to be a set of probabilities. Now, since I have multiple outputs here, it becomes kind of difficult to have multiple categorical cross entropy losses, right? So it becomes important to define a slightly different loss function to train my network. So let's talk about the loss function which we're going to use to train this. Okay, one moment. There is a question, guys. Let me take that up quickly. Vinay says, if we use multiple outputs, will it not create loss in context? Loss in context. Why would it create a loss in context? Vinay, if you notice, am I not training it to take big and tell me and dog over there. So is it not, isn't the context information being captured by the sliding window? And I'm asking my network to now predict it. I don't see how it creates a loss in context. Could you please be more clear? Like, okay. According to me, it will not create a loss in context because I have essentially asked it to predict the words around the central word. So I'm capturing contextual information through this way of generating my training data. Okay. Okay. What if we have but not dog for big word? But we do have that, right? I mean, when I'm creating my training data, because a big dog appeared in my training data set, I'm going to have and dog both, right? So it is a way for me to extract these triplets or whatever size that I want by shifting this window. Vinay, I think what you're trying to ask me is, is it not possible for me to, okay, maybe what you're asking me is, how am I capturing the position? Is your question, we lose positional information or contextual information? Is that your question, Vinay? Is your question positional information? Okay, let's do one thing, Vinay. Please put up your question on the questions tab. Try being as precise as possible. I will take up your question in the doubt session. For now, I would like to continue. Okay, if that's okay. Is that cool? Is it okay if I continue? I'll quickly take up your. So please put a question in the questions tab, because I think what you're trying to ask me is positional information. I will have that discussion with you in the doubt session. Okay, cool. So now, for now, let us come back to the problem at hand. I now have to design a different loss function here. Okay, I have to design a different loss function here. So for skipgram training, right, we no longer want to predict a single word. We want to predict multiple words. So essentially now what I want to do is I want to maximize the probability of getting one word, or I want to maximize the probability of getting the words around this word, given that the current word is WT, right? So the loss function that I will design for my skipgram training is now this kind of a log likelihood loss. So this term is known as log likelihood because we are asking for the probability of WT plus J given WT, right? So if you remember Bayes' theorem, we had those likelihood terms and all those things. So if we just take the log of the likelihood term, which appears on the left-hand side in Bayes' theorem, it becomes this log likelihood. And this is what we try to maximize when we're training this. Why are we not doing softmax and CCE? Because we don't want these probabilities to sum to 1. We want these probabilities of this word to be independent of the probability of that word. I want the probability of this word to be independent of the probability of that word, which is why now I have to design this kind of a loss function to train my neural network. Okay, cool. Now, this is one absolutely possible way of doing this, but it turns out that training skipgrams with this kind of becomes a bit inefficient. So there's actually this other strategy called negative sampling. So we're going to discuss this a little later. I just wanted to sort of tell you that this is not the only way of training my skipgram. Okay, there is a slightly better way, which is known as negative sampling. We're going to come to negative sampling slowly. Before that, I want to show you guys an example of what the output of a Word2Vec would look like. Okay, let us assume we have implemented all of this. We have trained our network, and now we have gotten the embeddings for all the words which are there in our corpus. Okay, imagine that all of this has happened. What will our output look like? So there is this excellent website which tells you, which sort of shows, which sort of captures this embedding. So let me quickly just share this link with you. If you guys are interested, you can play around with this embedding. What is nice here is what these TensorFlow people did was they took a 10,000 length hidden layer. Okay, they took a 10,000 length hidden layer for a very, very large vocabulary size, and they trained it. Once they trained it, they got all those 10,000 length vectors, they applied PCA on it, and what they're representing here is 3 components. The total variance described by this representation is 8.5. So it's not that reliable. Okay, so this visualization is not that reliable, but let us see how well we do. Okay, So if I hover on this visualization, right, I will basically get the name of my vector. So I have this vector explosive, I have this word explosive here, right? So if I click on this word explosive, it will basically give me all the words in this space which are close to that word explosive. So the words which are really close to the word explosives is powder, explosion, blast, firing, weapon, bomb, gases, liquid. So yeah, right. So essentially, this is what we get, right? Effectively, this is what we get. So Indradeep, is his question is, can we apply TSNE on this? We can try. It's just that if I click on this button, right, it takes a really long time for this to happen. So I don't want to do this now. I request you to play around with this like on your web browser later on, right? For now, I just want to sort of see the uh, this thing structure of this. So what's nice is now, if we actually go ahead and do this kind of training, what I want you guys to notice here is, if I now look at the closest vectors to this single word. So if I take the single word psi, the closest thing to this word psi is all of these: r angle, sigma, math rm. Okay, so guys, this is a little bit of a contextual thing. In LaTeX, right, backslash psi is the Greek symbol psi. So all the things that we're seeing which are close to this psi are LaTeX symbols. Okay, so R angle is basically the LaTeX symbol for that. The less than. R angle is this one. Yeah, R angle is a right angle. L angle, right? So basically, you have these brackets, right? The angular brackets. So this R angle, L angle are that. Okay. So this tells me that psi and phi appear very close together. This is because of wavelets, and R angle, L angle because they represent the inner products. So essentially, that is how we interpret this. Similarly, if I click on the word drawing or conspiracy, actually, let's click on conspiracy. That seems like fun. So if I click on conspiracy, the words which are very close to conspiracy are murder, assassination, alleged, theories, and etc. Right? So it turns out that if we apply the strategy of skip gram on a size 10,000 Word2Vec representation, this is what we get, and it's quite decent. So let me just click TSNE. It is going to take some time. Maybe we can explore this at the end of the class, Indradeep, if you're interested. I'll just keep this running, and it takes a little bit of time for it to animate. So let's just wait for that. In the meantime, let us go and discuss some other things about our skip gram. Okay. Um, so what we have to understand is essentially negative sampling. We'll come back to this. I'm going to talk about negative sampling and its uses a little later. First, let's come back to our problem at hand, right? What we have to do is semantic search. If you give me a certain set of keywords, I have to give you the most relevant papers with respect to those keywords. And what we have seen is that seems to be happening over here, right? If I have this kind of a representation, I can basically look for all the words which are close to this, and I can give you a paper based on that, right? So let's see how to do this now. Okay. So once again, what I'm going to do first is I'm going to create this df underscore COVID. What this df underscore COVID is, it's going to have only the relevant columns for my problem statement. So I'm going to keep paper ID, title, abstract, and DOI over here. Ajay, like somebody had suggested, right? We should return DOI. So just for that reason, we're going to keep this DOI. So your suggestion is actually considered over here, right? Okay. So I now have this data frame COVID, which keeps these columns from my original data set, right? So this is what we're going to construct our data set from. The info of this is over here. There are a lot of null values over here, right? So out of 1 lakh entries, only 35,242 are non-null, right? So the first thing we would probably have to do is drop the duplicate stuff here. So once we drop the duplicates and null values from this, right, we end up with just 29,458 entries in our thing. Okay, so it does look like in our data set there are a lot of duplicated papers. Why this has happened is not very clear. One possibility is that generally what people do is they will put their paper in archive once they've finished writing it, and then they will submit it to a journal. So because of that reason, we could have a lot of duplicates over here. So yeah, we essentially got rid of that. Now we will focus only on publications in English and drop anything that is not English. So if you remember, guys, I told you about this lang detect library, right? So this is where we are going to apply that lang detect library. Okay. So from lang detect, if you notice here, I'm importing these detector factory and detect function, right? So let's now apply this library to detect only those papers which are written in English. Okay. The way I'm going to do this is as follows. First, I'm going to say detector factory.seed equal to 0. The reason why I'm going to put seed 0 is because I want reproducible results. So if you guys run it, you should have the same results as if I have it. So we set that. Then we create a loop over here where we first select just the first 50 words. Okay. We will first use just the first 50 words of my abstract to do this language detection. uh, if the algorithm is not able to reliably detect a language, right, it usually throws an exception, which is why we have put this lang equal to detect thing inside this try catch block. Okay, so let us suppose the first 50 words are not enough for this to detect the language. Okay, let us assume that the first 50 words are not enough to detect the language. Then we have to basically pass all the words to this detect function and get it to detect the language. Finally, if it is not able to detect the language in spite of all that, then we will just say, okay, we'll give up. We'll say this is an unknown language. We won't even bother with this paper. Okay, that is how we're going to apply language detection on this. Now, this strategy takes a little bit of time. It took 3 minutes to run. So once we run this, let us sort of see the distribution of papers over here. Okay, so we have 51 French papers. We have 4 PT. I'm not sure what PT is. PT is PT language encoding. Yeah, PT language code is this, right? Yeah, PT is Portuguese. Okay, so PT is Portuguese. So there are 4 Portuguese papers. There are 29,261 English papers. There is one Chinese. Is this Chinese? Let's see. CA. Oh no, it's Catalan. So it's basically no Catalan Indradeep. Catalan is basically another language in Spain. Yeah, FC Barca fans will know this. So yeah, okay. So then we have NL. So basically we have a lot of papers here. What we're going to focus on is just the English ones. Okay. So now let's see. Since most of the publications are in English, we can safely drop the rest. We're not going to bother with the rest. We're going to apply Word2Vec training only on this. Okay. So let's do that. df COVID equal to this, df COVID of language equal to en. Okay, so these are the papers. Now we do not need the language feature column, so we're going to drop that. Like we had created this feature vector, right? To basically drop those corresponding, to drop the corresponding column rows. To drop the corresponding rows, we had created this. We're now going to skip that. We're going to get rid of that, and we have this. And finally, we now are going to use our usual text processing pipeline to get rid of punctuations and stop words. Okay, so stop words is essentially this thing. So stop words comes from the stop words library, right? The NLTK stop word library. So I guess it is defined somewhere up. Let's go and check this. Let's quickly check this. Stop words should, So no. I'm sorry. The stop words are coming from the spacey stop words. So spacey.lang.en.stop words import capital stop words. So this is coming from spacey. So we're going to take spacey's stop words. We're going to get rid of those. And then we're going to have some custom stop words. Okay. The reason why we're going to have custom stop words is because our data basically contains papers, right? So there are some typical words which are there in papers which don't really have much sense. So now what we're going to do is we're going to get rid of those specialized stop words. So let's quickly go and see what those stop words look like. Yeah, they look like DOI, preprint, copyright, peer, reviewed, ORG. So basically all that extra information that is there in a paper, right? Uh, like Elsevier and these kinds of things that we're going to drop from that. Once we're done with that, we put everything together in this preprocess function and we apply this preprocess function to everything, right? To all the abstracts in our data frame. Okay, that is what we're doing here. Progress apply preprocessor on all the rows of my data frame. So once I've done that, I will essentially have a data frame where I only have the keywords which are present. If you notice, I'm going to have the keywords present in the right order, right? So that is also kind of important to remember. And then using this data frame now, we're going to train a Word2Vec model. Okay, cool. So we're going to do a little bit of like management of our this thing here. So we're going to basically tokenize our sentences and all that. We're going to basically continue applying different pre-processing steps so that it becomes easier to apply Word2Vec over here, right? Okay. So this essentially just creates a list of words from everything. And now let us create our own Word2Vec model by training on this corpus. Okay. So let's come back to the discussion of negative sampling a little later. Essentially, guys, what I'm using to train this Word2Vec is this library. Okay, there is this library called Gensim, and from the Gensim library, we're using this Word2Vec function. So let us quickly go to the documentation of this function and see what this looks like. Okay, so this is the Gensim library. We're using this library to implement Word2Vec. The parameters that we can specify are sort of given over here, right? So let us see what are the settings that we have made for our Word2Vec. So the input that we're giving it is this Word2Vec corpus, which is nothing but this list of words that are there, right? Once we have that, the min count we are specifying is 3. The min count over here basically tells it to ignore words which have occurred less than 3 times. Okay, it's possible that such words are not very important because they're very specific to that paper. So we have basically asked this algorithm to ignore all words which occur less than 3 times. Then we are specifying the size of our hidden layer as 100. We are not going to train it to 1000 because it takes really long to do that. So we've kept the size to 100. We're saying use 4 workers. So the workers basically tell it how many processes to use, right? So it is going to use 4 threads to do this. The window function size, right, is specified over here. We're going to use a window function of size 5 for this. SG is okay. So let's quickly go to SG and see what that parameter means. So SG over here is the training algorithm. SG basically is 1 for skipgram, and it is 0 for CBOW. So obviously we want to try skipgram, right? We don't want to try CBOW. And the final parameter here is negative equal to 5, right? Let us see in the documentation what this negative equal to 5 means. Yeah, here. So the negative sampling will be used. Int for negative sampling specifies how many noise words should be drawn, right? Now let us come and discuss what is negative sampling and how we are making use of this over here. Okay, cool. So now specifically we're asking our Word2Vec object to use negative sampling to train our network. What is negative sampling? It is a way for me to sort of reduce the computational complexity of the softmax layer. Okay, so let's talk about this for a bit. So for a large corpus like we have, right, the vocabulary size will be on the order of 10 to the power 6, right? It will be on the order of millions. No, actually, no, not millions. It will be more like 100,000. So it will be on the order of lakhs. It won't be on the order of millions. So my vocabulary size will be somewhere around here. I want to ask you guys something. What is the computational complexity for the softmax layer? So softmax is basically defined as e to the power zi upon summation k going from 1 to mod v, right? Because we have those many vocabulary vectors, k will go from 1 to mod v. I will have e to the power zk in the denominator, right? So can you guys quickly looking at this tell me what should the time complexity be for calculating the softmax for one input? What's the time complexity? Mod v, right? This is basically big O of mod v, right? So exactly. So since this softmax computation is big O of mod v, if my algorithm, sorry, not my algorithm, if my vocabulary size itself is on the order of 10 to the power 5, for each input vector during my training, I will have to use this kind of time complexity to do it, right? So this is very, very intractable. Intractable means this will take very long. So instead, right, instead what we do is we create negative samples from a certain window itself. So now instead of putting mod v in the denominator, what we are going to do is we're going to make things slightly more sensible for our network to do. Okay, let us see the formula for this negative sampling first. Okay, let us quickly see the formula for the negative sampling. The formula for the negative sampling loss function looks like this. Okay, so let us try and understand this. The new loss function with respect to which I'm going to train my skipgram network is this one. Argmax with respect to theta, summation w comma c belonging to d, where d is my corpus, w is a word, c is another word, right? The comparison word. I have log of sigma of vc dot vw. Okay, the dot that you see here, guys, is the dot product. This vc is nothing but the vector. Okay, this is the output vector for this word. The output vector of w is vw. The dot product is over here, and sigma is nothing but sigmoid. Okay, sigma is nothing but sigmoid. What sigma does is it basically makes sure this dot product comes in the range of 0 to 1, right? This dot product comes to the range of 0 to 1. So that is what we have over here. Similarly, we have another term now. Okay, now look at this. I now have w comma c in d prime. Okay, so now I have changed the set over which I'm computing this loss function. So let us see what this d prime is. The d prime over here is essentially the negative set, right? How are we going to construct this? I'll come to this slowly. First, let's focus on the functional form of this loss function. Again, I have log of sigma of, the sigma is again the sigmoid, minus vc times vw. So what I want you guys to notice here is I'm forcing this inner product to be negative, right? I'm forcing this to be negative. So now let us try and understand why this is done. Okay, why this is done. So do you guys remember that the dot product is nothing but like a scaled angle between the two, right? It's like a scaled angle between the two. So if I now have these two vectors, right, v and w, okay, since the angle between v and w is the same, can I expect the cos of theta to be 1? Can I say that the cos of cosine similarity between v and w is 1 over here? Do you guys agree? Cosine similarity between these two is 1? Okay, cool. When is the cosine similarity minus 1? When is the cosine similarity minus 1? Is it minus 1 when I do this? Okay. When I answered it already. When I said it's opposite, right? So when it is perpendicular, right? This is actually 0. This is actually 0. The cosine similarity becomes minus 1 when they're pointing in the same, they're along the same line, they're collinear, but pointing in opposite directions, right? So for this kind of a setup, my cosine similarity is going to be minus 1. So that is why I'm basically forcing all the positive words, right? The positive words I want to force to be 1. The negative words, I'm trying to force them to be minus 1. So that justifies why I have put plus and minus over here. Now let us see how we are going to design our positive and negative sets, right? Okay. So let's sort of look at this example. So the skipgram over here, so this is basically a skipgram with a window size of 5. My central word is make. The words around it are not, shalt, and machine, right? So if my input is make, the output can be shalt, the output can be not, the output can be and the output can be machine. Now, these are the positive examples for my skipgram training, okay? The negative examples that I'm going to give it are basically words which are not here, right? So make and shalt should be 1. Make and Aaron should be 0 because Aaron is not appearing in this window, right? Similarly, make and taco should be 0. Why should it be 0? Because the word taco is not appearing in this window length over here, okay? So this is what I mean by negative sampling. I'm not only going to show it positive samples which I'm getting from that sliding window, I'm additionally also going to take, or I'm going to consider negative samples in the sense that I'm going to bring words from other places in my document and I'm going to create these training vectors. Okay, this is what I mean by negative sampling. So now let us come back here and understand this new loss function with respect to which we're optimizing. The new loss function with which we're optimizing is this one. So for all the words which are positive samples, I'm going to compute this term. For all the words which are negative, I'm going to compute this term. The sum of this is what I'm going to optimize. Okay. Now let's come to this Word2Vec and see what this negative equal to 5 means. So what this negative equal to 5 means over here is basically for every 5 uh, words in my positive sample, I'm going to have 5 words in my negative sample. So I have selected 5 here because I had selected 5 as my window size, right? I basically want to make sure that my class labels are balanced. So that is why I'm selecting a window size of 5 and I'm selecting a negative sample size of 5. So now I have a balanced training data set. It is possible, maybe if we want to use this for a specific application, it could make sense to change these numbers, right? So that's the idea. Bishwarup's comment here is, it seems like this is done to reduce overfitting. Perfect, Bishwarup. Yes, that could be one of the reasons why this is done. It definitely makes sense that if I give it negative samples, it will try to avoid those mistakes, right? So it makes sense there. Indradeep's query is, negative sample is for reducing computational complexity or reduce overfit. Indradeep, it is specifically to reduce time complexity. When they first proposed it, right, in the paper which first proposed it, they did it for reducing time complexity. But a side effect could be the overfitting reduction. It does look like that. It makes sense to think of this as a way to reduce overfitting. But primarily, when the paper was published, it was proposed as a way to reduce the time complexity for that. Yes. But in skipgram, are we using CCE loss? No, Indradeep, we're not, right? So before this loss function, we were using a different loss function, right? We were using just this part. So let us say we were not doing negative sampling, right? Let us say we were not doing negative sampling. We would just be focusing on this loss function, right? We would be focusing on this loss function. Why this loss function? Because of the following thing, right? We're using this loss function because essentially what we wanted to do was we wanted to maximize this. So maximizing this is essentially giving me this, right? So that's the idea. Indradeep, is this clear? What we will do if we don't give negative classes, this one. Okay, cool. Now, Vinay's question is, are we doing more calculations? How are we saving time? Vinay, we're saving time by not using softmax. Vinay, if I had to compute softmax, I'd have to do a big O of mod V operation. Okay. Now, since I'm not requiring my final layer to have softmax, instead, to enforce the probability term, I'm putting a sigmoid over there, if you notice, right? However, instead of softmax, what I'm doing is I'm passing it through a sigmoid non-linearity, right? So this is how I'm saving on my calculation. Is that clear, Vinay? Okay, cool. So I'm saving on my calculation by not computing the softmax. Instead, I'm going to pass it through a sigmoid. Okay, cool. So let's go ahead now. Now, once we have specified all of this, we will essentially train this. This takes about 10 minutes to train, guys. You can try running it later. I had run this earlier, but unfortunately, like the runtime got disconnected. So I'm going to just show you the results. And this usually runs silently. There is no debug messages that it gives unless you specify it to give you debug messages. So this was run silently, which is why we don't see anything here. Now, moving on, what we're going to do now is, once we have this kind of a embedding, right? Now we have a model which is giving us a vector for every word that we're giving to it as input, right? So now what we will do is we will have a mapping between words to vectors. So now the question is, now how do I use this mapping to actually do my task, right? How do I do that to actually do my task? Let us see. So let us take an example. Let us take this as our example. Okay. Let us say that my query is origin of coronavirus. Okay. Let us assume for now that this is my query. So the strategy that I'm now going to apply, so there are two issues here, right? How to encode this, and problem number 2. So this is issue number 1. And if you guys remember, we had a corpus sitting here, right? We have an entire corpus of documents sitting over here. So we have D1, D2, D3, so on. Let me be consistent. This was n, right? Dn minus 1 and dn. So the second question is how to encode these. Okay, this is the basic problem here now. Fine. So guys, now what we have is basically a machine, right? Which if you give it one word, it will give you a vector, right? We selected a vector size of length 100. So if I give this machine, if I give this skipgram, if I give the skipgram Word2Vec a word, it will give me a 100 length vector. The question is now, how do I start encoding these things? So it's kind of simple, guys. What we do is we essentially take the average of all the words that are there over here. Okay. What is nice about an embedded space is you can take linear combinations to get to points which are close to all of these words. So I want you guys to sort of think of it this way. Okay. Coming back to this visual example over here. Okay. So okay, now this is still moving around. Let us sort of switch back to PCA for now. It'll not move around so much. So let me use it here for now. So what's going to happen is, let us say that my embedding space looks like this. Okay, let us say that my embedding space looks like this. If I now want to encode this origin of coronavirus, what I'm going to do is I'm going to take this query, I'm going to take the average of all the vectors that are there over here, and I'm going to get a vector in a certain direction, right? So I'm simply going to take this word's vector. So let me say this is v1, this is vector 2, this was word 1. I apply skipgram and I get vector 1. So w2, w3, w4. I get v1, v2, v3, v4. Now to encode this line, right, what I will do is I will say 1 upon 4 times summation of vi, where I goes from 1 to 4. This will now be my encoding of this thing over here. And same way, what I'm going to do is I'm going to create the same kind of embedding for these things. Okay. So now every document which is there over here, I'm going to take the words over there. I'm going to compute the average of the vectors which are there, average of the vector form of the words which are there in that document. I'm going to take that, and that new vector is going to be my vector representation for the document. So this is how I can go from a vector representation, a word vector representation, to a document vector representation, right? This is how I can do that. Once I do this, I simply have to now calculate all the documents which are close to this averaged vector, and that will finally give me my answer. So let's implement this and see how effective it is. Okay. So coming back here, to calculate the centroid for each abstract using the vectors of all the words incorporated. So this is me encoding the entire corpus that I have. To do that, what I basically have to do is I simply have to take the average of this, right? So if you notice here, it's nothing but np.add of this, and then I'm going to do that. So, okay, over here, they're not taking the average. They're simply taking the sum. It's possible for me to normalize this. It will only change the magnitude in that space. So as long as I'm consistent, I should be fine. So over here, we have chosen to add everything over here. Okay. Now, once we have created this kind of a representation, to actually create a rank of this, we have to search within this, right? I have to basically go and look at the cosine similarity between my query vector and this vector. So this rank docs is basically going to do that k nearest neighbor search on this one. So this is that implementation. And finally, I have my query over here, right? So my query is basically here. What I'm going to do is, again, I'm going to just one moment. Query equal to query dot split for q and query a dot append model of q. So again, this is going to give me a model vector. So again, I'm going to compute my centroid. Then I'm going to find the closest one with respect to that centroid, and then I'm going to get the output, right? So once I apply this strategy, let us see what happens for origin of coronavirus. So the results that I get are as follows. Role of non-structural proteins in the pathogenesis of SARS-CoV-2. Now, this is very interesting, guys. Origin of coronavirus is the query that we sent, and the word that it picked up from my titles is pathogenesis, right? The word pathogenesis means uh, the the origin of the this thing. So pathogenesis is basically a word which represents how this got originated, right? So it has mapped this abstract idea to a word which is actually there in the title of the paper. So this is quite interesting to us because it's now actually doing the job we set out to do. Given this query, we are able to return a relevant paper. Let's look at the titles of a few other papers. We have re-emergence of a genetic outlier strain of equine arteris virus, impact on phylogeny. So again, this seems to be quite relevant to corona, the origin of the coronavirus, emerging and neglected virus of zoonotopic importance in Croatia. Okay, I'm not sure what that means. Global emergence of severe acute respiratory syndrome in coronavirus 2 and the human. So yeah, again, what I want you guys to notice is it's talking about the global emergence of certain symptoms of the coronavirus, right? So it is actually able to take this input query that we are giving it, and it is giving us the correct output from that. Okay, it's taking this input query and it is giving us the correct output from that. So in conclusion, we have actually managed to solve the problem that we started out by doing this method. Okay, so this sort of ends the demo of our method, and now we can make our concluding remarks, right? So essentially, continuous text representations are used to capture syntactic and semantic similarity. So what the major change that we've observed in today's method as opposed to last week's method was that we are now able to capture semantic information from this query. It's no longer just the keywords which are appearing here, right? There is now semantic meaning from the query that is getting returned from the method that we have just applied. So that is the most striking thing over here, right? Okay. We basically studied SVD methods, which served as the origin, which served as the inspiration for these Word2Vec type of architectures. We saw two variants of Word2Vec. We saw continuous bag of words and skipgram. We saw two types of training methods for skipgram. Negative sampling is what we saw. Hierarchical softmax is something that you can sort of study in your post-treat. It's simply a way to apply softmax in a way that uses a binary tree or a binary string to represent each word. So the way we are representing the word changes there, and it helps us sort of improve the computational complexity of the whole thing. So that is something that you guys can study in the post-treat if you are interested. And fundamentally, the final thing that we sort of the final technology that we used was this GenSim library, right? We used the GenSim library to do this. Instead of sort of implementing Word2Vec from scratch using Keras and all that, we have this nice library which does everything for us. And using this, we built a search engine based on semantic similarity between query and abstracts of publications. So in case you ever find yourself, worrying about which paper to read first, you can actually build something like this for yourselves and use this to search for relevant papers. So it's like you're solving your own problem instead of relying on stuff like Google. But honestly, Google Scholar will probably give you better results. But if you have like a set of work-related documents which you can't really Google on, this could be one nice way to sort of search on top of that, right? So yeah, this sort of concludes the content that I have for today's lecture. And I'm going to now start the doubt session for today. So if anyone has any doubts, please go ahead. You can ask me your doubts now. So I believe Vinay had a doubt, right? Vinay, can we go back, revisit your doubt from before? I believe your doubt was regarding this, right? How are we storing positional information for this representation, right? Okay, that's clear. Fine, awesome. Cool. So if anyone has any doubts, I'll stick around for maybe a minute or so. Otherwise, we can end today's lecture. So it's interesting, guys. So last class, we built a representation which did not have semantic information. This class, we built a representation which has semantic information, but maybe the position is not that great, right? The positional encoding of this is not that great. The only thing we're using for positional information is the location of the output vector. Now, this is not great in terms of predicting what should have been the word before this. So what we're going to see is, in the next class, we're going to start talking about representations which actually help capture these positional informations better, right? So we're going to solve a problem called language modeling or topic modeling, one of those. We're going to solve that problem, and we're going to slowly start building our way to representations which are able to sort of predict what should the next word be, right? Things like chat gpt. So if you give a query, it is able to give you an answer based on some mapping of how the ordering of the word should be. So the technology that actually goes into this is long short-term memory. So the first intuition was long short-term memory, which came from time series analysis, right? Just like you have auto-regressive models which use previous samples to predict the next one, you have these long short-term memories which will help you predict the next word. And then the advanced version of that is the transformer network, right? Which helps you capture long range relationships as well. So that is what we're eventually going to build up to. Cool. So I see that there are no further doubts, so we can end the class here. Thank you so much, guys. Oh, okay, wait, there's a doubt now. Vinay has a question. In skipgram as well, if used combination of words is so frequent, which are of wrong context, our embeddings are not so great, right? Yes, Vinay, you're absolutely right, because it's like we're confusing our network by giving it so many possibilities, right? So the only information that it can use to predict what should be the close by words are what are the most frequent occurrences. So the frequent combinations are weighted more than probably the more sensible combinations. So you're right about that. So this is exactly the problem I was just talking about, right? What we are focusing on is the local context here, but in a text, right, it is possible for us to have global context. So now we have to figure out a way to sort of bring global context into the local setting, right? And that problem is somewhat solved with BERT, the architecture. So once we get there, we'll sort of see how we are able to capture long range connections as well, right? And in fact, LSTMs also solve it to some degree. Yeah. So, but I'm really happy that you noticed that the locality is very nearby. The locality is fixed very close. We're not actually getting context from beyond the window. So we're going to see how to fix that with different architectures. Cool. Okay, guys. I'll see you again next time on Friday. Good night.